continue with the lecture today. Actually, this will be the discussion for the assignment number 1. I'm going to go through this one later, and again to show the steps of the solution we're going to have for the assignment. Okay, so we said to design the hooper and the pin. We need to do the following steps. We need to do the measurement. We need to do the measurement. We never use the tabulated data for the materials because we said that the interparticle fractions, which done by the cohesion of the materials, is going to be different from one place to another, from different condition to another, different material to another, and of course from one time to another. So we need to do the measurement for that. Also, we need to check what will be the wall fraction for the material with the wall of the silo, and we need to check the compressibility and the permeability of the material. That's an extra test actually. It's something like they put the material under a certain pressure for a certain time, and then they do the measurement for it. The same two measurements is going to be done for the compressed material. The last one, the first two actually, is going to be data used to check, to do the measurement, the calculation for the outlet size, the hooper angle, and for the massive flow and discharge rate. But for the compressibility and the permeability, is going to be the measurement to be done to know what will be the maximum time we can leave the material inside the silo. So we learned about the angle of the repose earlier. We said that the angle of the repose, or the critical angle of the repose of the granule materials, is the steepest angle. The steepest angle we're going to have of the descent of the dip relative to the horizontal plane, to which the materials can be piled without any sound, without slumping. So if I'm going to have very fine materials, it's usually going to hold itself. But again, to have a coarse material, it's always going to do so. This can help me actually to choose what will be the material handling system I'm going to use, and as a selection, because we said that we have a wide range of the material handling system, and we need to choose a different one for depending on the material we're going to use. The thing is that the angle of the repose is not going to be an adequate indicator for the bin design parameters. It can help me, but it's not going to the main parameters. The other parameter is what we mentioned earlier. So the angle of the repose, in fact, it is the angle of the repose is only useful for the determination of the contour of the pile, and it's popularly among the engineers and the investigators is due not to the its usefulness, but due to the ease at which it can be measured, and that's what Andrew Jenkins said. So he described that, okay, it's easy to be measured, it's easy to be done. So we had, for example, at the beginning, the assumption that the angle of the hooper should be more than the angle of the repose of this material. This can be a good indicator, but it's not going to be a useful design procedure. So we don't use the angle of the repose to design the angle of the hooper. And we need to start with doing the testing for the bulk solids material. So one of the tests we learned earlier was the wall friction testing. We talked about it last time with the Jenkins shear test. And also we can do the powder shear testing, which is a measure for the both powder internal friction and the cohesion of the materials. And we do the compressibility and we do the permeability. The source of the cohesion we have in general are going to be the solid bridges, like the mineral bridges, chemical reaction, the partial melting, the binder hardening, the crystallization of the materials, and the sublimations. We may have the interlocking forces. The particles doesn't have the equivalent shape, so it's going to tend to lock with each other, hold each other, and stop it and slow them down and give it the build-up of the materials. We have the attraction forces like the van der Waals, the electrostatics and the magnetics, and we have the interfacial forces like liquid bridges or the capillary forces. The consideration factors in the test are going to be the following variables. First, the time, the temperature, the humidity, and other process conditions. So usually we're going to have more constellation to be having for the material. The material is going to be more cohesive. It's going to be stored for a longer time. So if I get to, for example, grind the debris to have a flow, the flow properties when I just made it, it's going to be different from its properties after 2 days or 3 days, because we have time factor, we have temperature. Of course, we are going to have some humidity in the air. So to do the testing, as we learned in the lab today, we're running what we call the wall fraction testing. The device we saw in the lab today is exactly similar to that. We had the ring, it was a box in the lab, and we had the cover, and we applied the normal force at the top. So this will cause the direct stress on the material, or what you call the normal stress on the materials. It will tend to compress it. And then we can add a horizontal force. It's called the shear force. The shear force is going to be equal to the fraction of the wall material sample with the material. Okay, so the amount of the force we're adding here, and we can measure, is equal to the friction force between the material, powder sample, and the shear force, and the sample wall material. So this will simply going to help us to find the shearing occurs between the powder and the wall sample. We can add another ring, okay, and the two rings can be sliding over each other, and this will give me the internal friction of the material, because you can see the sliding is going to be happen between the material particles, not the material with the surface. This one is going to be static here. So one of the most common test apparatus is the Jenkins shear test, and we are going to have the example for it and the question number 1 in the assignment number 1 using a result has been actually extracted from the Jenkins shear test. What we can notice is that if I'm going to add more forces normally, this will increase the shear force. That's very simple. If I'm going to put my hand on the table without any pressure and try to pull it, I'm not going to have too much resistance. But if someone going to put his hand over my hand, press it over the table, I'm going to have some difficulties to pull my hand. So that's what we had in these two tests. We're going to have the first force divided by the area of the cover. This will give me stress. And I'm going to measure the shear force, and divided by the area, I'm going to have the shear stress. So I expect to have higher shear stress every time I'm going to add more applied weight. So we are going to have a relationship between the sigma and the tau to go up as the value of the stress is going to be increased. The shear stress is going to increase. From these parameters, I can sketch the Mohr circle. By finding the Mohr circle, I'm going to find the sigma 1, which is the maximum stress, and I can find the sigma c, which is the critical stress, which is going to force the material to move or initiate the movement of the material. So the powder sample is going to be placed in the sample holder. The movement of the sample holder causes the shear between the powder sample and the sample of the Huber walls, as we can see in the figure A, to determine the wall friction coefficient. To show you how to do this calculation in the tutorial. Or The movement causes by the shear internally in the powder samples as in figure B, and this will be the internal coefficient of friction. Both values are going to help me to find what we call the flow function, or the FF we learned last week. And actually these values has been tabulated for different delta W and delta, or theta W and theta actually. And we're going to see that in the charts I'm going to describe to you soon. Okay, so these are the wall friction testing devices. You can use everything we talked about right now and writing down your lab report next stage. The wall friction testing have the following relationship. The force, or the friction force, is going to be equal to the coefficient of friction of the table, or the sample of the wall, multiplied by the normal force. That's simply going to explain to you what I just mentioned. If I'm going to put the pressure, okay, on the surface, okay, now I'm going to try to move the phone over my hand. Now it does have a friction, coefficient of friction from my skin and the phone surface. And the weight of the phone is the only normal force we have on my hand. So to calculate what is the force I'm using to pull the phone is going to be equal to the coefficient of friction multiplied by the weight of the phone. Now if I'm going to put an extra weight on my phone, I'm going to increase N. I'm going to increase N, and thus the force will be increasing. If I'm going to add a layer on my hand, which is going to have a rough surface, I'm going to increase the mu value or coefficient of friction. And then the force required to pull my phone is going to be even higher because the mu has been increased. So just remind you about that. So as a common, the value of the angle of the wall of friction is going to be a factor of the coefficient of friction. So the angle of the wall of friction is going to be equal to the tan inverse of the coefficient of friction. Arctan, which is actually the tan inverse. Okay, tan inverse of the mu is going to be the wall friction angle. So the wall friction angle can be determined as following. We have the shear stress and we have normal stress, and the angle of the line between them is going to be equal to the delta wall, or the wall angle between the material and the wall of the sidewall. So after a number of values has been recorded, the wall yield locus is identified by plotting the shear stress against normal stress. Angle of the wall of friction, delta W, is the angle that is formed when the line is going to be drawn from the origin of the graph, from the 0, 0 point, to the point of the wall yield locus. And that's what we're going to learn by using the SolidWorks. So for the powder technologists, usually express the mu, which is the Hooper angle, as a function of the angle of the wall of friction, and they simply going to find that the delta W is equal to the tan inverse of the coefficient of friction. So if you're going to have different types of the Hoopers, like the conical shape or the cylindrical shape, we're going to have different values for the wall of friction according to the angle from the vertical of the Hooper we're going to have. So this will be the angle. It's going to depend on the value of the wall friction. Usually, as you can see here, that the higher angle is going to be required if we're going to have a lower wall friction angle. So we're going to go through this one during the design. This actually just repeating the same thing. So I prefer that. So actually, the process is going to be as following. We do the test. We find the wall friction angle, and by using the parameter, depending on if we're going to use the conical Hooper or if we're going to use the planar Hooper or the cylindrical Hooper, what will be the Hooper angle from the vertical in degree is going to be found. So below this line is going to be for the massive flow. Above this line is going to be for the fuel flow. Now for the shear test, once again, just to remind you about it, we can either have it as the shear plane, it's going to be a horizontal movement, or we can have it as a ring shear test that is going to rotate the materials in another form. So after we getting the shear stresses and normal stresses from the test, we can sketch the Mohr circle. Now, for example, here we've got 4 tests, and we sketch this line. This value is going to be the C value, and by sketching the 2 more circles, we are going to find the sigma 1, and this one is going to be the sigma C, or the critical stress required to move the material. Once again, I'm going to explain that in an easier way later. The common cause of the failure in the silo is the shock load during the arc collapsing. So when you have the arc formed and hold the materials, then suddenly it's going to be collapsed. So the material is going to be leaving suddenly, and this causes different pressures in the silo, and this will cause the collapse. Because we said once again, it's just galvanized plates and is fixed by using the bolts. And these bolts, again, it's actually designed to hold the system, but it's not going to be strong enough to take off the shock, and it's going to be damaged. Also, we may have a bending in the cylindrical wall, and we may have the overpressure due to the change in the cross section of the material. The stresses we have in the hoopers in the silo, and the cylindrical silo, we're going to use the Jensen equation, and the conical section hoopers, we use radius stress field. In our case, the stress means the pressure inside the material. We usually, starting from the principle of the stress in the cylinders, we consider that we have a cylinder filled with liquid. But we're going to use the same equations and derive the what we call the Jensen equation. I don't want to go through that, but of course you know the concept that we take a section and we start to work on this section and derive the equation at the end. We consider that the high level will cause a higher pressure, as I mentioned earlier. Everybody knows that actually. I think if you remember that the old swimming, the old diving suits was actually having the armor at the head, because the pressure of the water as you go deeper is going to be higher. The same concept we're having here. So considering that, we are going to have the 2 key substitution in the equation, that the shear stress is going to be equal to the mu value, the friction coefficient, multiplied by the pressure on the walls. And the key assumption that has been taken by Jensen was that the pressure on the walls is equal to the K constant multiplied by the pressure due to the volume. Substituting and rearranging, we're going to end up with this equation, that the pressure is going to be equal to the density multiplied by the gravitational acceleration multiplied by the diameter of the silo we would like to have, divided by the 4 mu K, all multiplied by 1 minus the exponential of minus 4h multiplied by mu multiplied by the K divided by d. That's what we call the Jensen equation, and that's what we're going to apply in the question number 3 in the assignment number 1 to calculate the pressure that can be taken by the silo with identified height and diameter. So the equation is going to be explained as following. That's what you are going to use in your calculation. Definition of the parameters we have are, first, the D is the diameter, H, or the Z here is the height of the silo, G is 9.81, rho is the density in kilogram, rho is the density in kilogram per cubic meter, and you can find actually that from the material charts. The mu is the tangent of the delta W, which is a function of the wall refraction. Delta W is the angle of the wall refraction. The K is the Jensen coefficient, which usually is assumed to be 0.4. And finally, the GC is the conversion factor. That's every 1 Newton is equal to 1 kilogram meter per second square. We're going to have an example on this equation, which is going to be similar to the question we're going to have in the assignment number 1. Okay, so something happening with the I don't know what's happening with the anyway. So this will be the, if I'm going to consider that the things as a liquid, where you can see that at the top here, we're going to have the zero pressure. And as we go down, the pressure is going to be increasing because the stress is going to be increasing, of course. So this will be the curve of the pressure we're going to have inside the bin. Now let's have an example on designing the silo by calculating the pressure we are going to have, and thus we are going to design what will be the diameters. We can change the diameter, or we can control the height, and also we can select the thickness of the plate we are going to use to make this silo, or the thickness of the wall we are going to use to build this silo. So the example we have in the front of us is we have a large welded steel silo, which have 4 meters in diameter and 20 meters in the height. This silo needs to be built. The silo has a central discharge on a flat bottom, so it doesn't have a mover. Estimate the pressure of the wall at the bottom of the silo. If the silo is going to be filled with first plastic pellets, or it's going to be filled with water. Now the difference is going to be the density, of course, and we're going to have different equation in the calculation if we're going to have water, or we're going to have the solid materials. So for the plastic pellets, have the following characteristic. The density is 560 kilogram per cubic meter. The delta wall, or the wall friction angle, is 20 degrees. So we have been given from here the diameter, the height, the G is constant, the density is given, delta W is given, so we can find the mu, and the K is constant of 0.4, and we can apply all these parameters to Jensen equation, and we can find the pressure. So we start once again, the mu is going to be 10 over 20, which is delta W, and then we can substitute everything in this equation. We're going to end up with that the pressure we're going to have at the bottom of the silo, we're going to use it to store the plastic pellets, is going to be equal to 35,668 Newton over meter square, or what equal to 5.2 psi. So just simple, straightforward application. This can be a question, and the assignment can be a question in the final exam or whatever. So just remember that the GC is 1, which is a conversion factor between the Newton to kilogram per second square. Now, if I'm going to use the water, the equation I can use is the pressure of the water. The equivalent pressure of the water is equal to K multiplied by the PV we just calculated, or 0.4 multiplied by 35,668 meters over meter square, and it's going to be equal to 14,268 Newton over meter square, or the 2.1 psi. So, sorry, that's the normal stresses. So if the cell is going to be filled with water instead of the granule, we're going to have the depth is given by the pressure is going to be equal to the density of the water multiplied by the G multiplied by the H divided by the GC. So density of the water is going to be 1,000 kilogram per cubic meter. The G is 9.81. The height is 20 meter, and we have the GC is 1 kilogram meter over Newton per second square. So the pressure, if I'm going to fill with the water, is going to be equal to 196,140, or almost 5 times than the pressure we have with the plastic pellets. Now, why we had this difference? Mainly because the density of the water is more than the density of the plastic. Also, we don't have the air gaps between the granules we have and the granules solid. So as a result, we that the factor is going to be about 13 times greater than the normal wall stress calculated in the case A. And this is due to the wall friction exerting the vertical upward forces on the granule solids. Now, I think you had something similar to this example on calculating the volume stored in the silos or the pins and the coolers. You can see that we have multiple stages. And to find out what will be the volume of the material stored, we need to calculate multiple volumes and add it up together. So we have the bottom cone height is given. We know the diameter, and we can get the volume of the bottom. We use this height and consider that this will be a cylindrical shape, and we can have this to be considered as a conical shape or the pyramid shape, and do the calculation. So the stored volume is going to be equal to the volume of the conical section plus the volume of the parallel section plus the volume of the resulting from the surcharge filling. So the volume is going to be applied by using this equation, and we can get what will be the total volume of the stored material inside the Now, the height of the cylindrical section can be found by using this equation. The height of the cylindrical section is going to be equal to 1.274 meter divided by the d square multiplied by the density, or which is going to be resulted as an, well, we can call it as an approximate to be equal to 0.385. So usually in general, we have an assumption that the height of the silo should be more than 4 times the diameter of the silo. So we had the example earlier that the 4 meter diameter got the height of 20 meters. Okay, so the total height, if we are going to consider the surcharge space at the top, it's going to be equal to the height has been calculated earlier based on the diameter plus 1.15 d. And of course, this will be more than 4 of diameters. The stored volume can be anything between each. So the height is going to be between the diameter less than 4 times of the diameter. We got this one earlier, but we are going to learn on how to make calculation for the flow creation and system. Okay, so we're going to go now for the types of the pin hand dehookers before we're going to start with the design procedure for the pins and dehookers. So the types of the hookers can be, as we mentioned earlier, conical shape with a conical hookers. It can be pyramidal shape with the pyramidal chisel shape at the bottom. We can have it which are the panel flow. In this case, we call the symmetrical shape hookers. We can have it as a chisel shape, which is going to be longer from one side. Which is going to have actually a symmetrical outlet, but it's going to be fixed on a cylindrical types of pins. And we can have the conical hookers, the square opening, the chisel, and the pyramids, and the wedge shape. Different types for different application. Okay, so these are even different types, and the most common one, of course, is going to be the conical one and the symmetrical one, and that's what we're going to learn on how to design the outlet size for these two types. Now, the next 20 slides is going to take us through determining the minimum hooker outlet size design. So the force acting on the powder, as we mentioned earlier, will usually tend to first, due to the weight, try to compact the powder downward. And this will reduce the bulk density. And we have the shear stress, and the material which try to tend to make it flow. This shear stress is what we need to overcome to make the material flow at the exit. Now, Jenkins' equation for the flow factor was the flow factor is going to be equal to the compact stress, or the sigma 1, or the normal force, normal stress we added on the sample, divided by the sigma A, which is the applied shear stress. Okay, so the flow factor is going to be defined as following. We do the graph sigma C, or the critical stress, okay, over the sigma 1, which is the normal stress. The FF value, or the flow factor, is the slope of this line. Slope of this line. And thus is going to be equal to what we have it in the previous equation, the sigma 1 over the sigma A. Now, if we're going to have the value to be increased, that means that the material is going to be cohesive. If this value of this slope, is going to be reduced, that means we are going to have the free-flowing material. Okay, so just remember that this equation we are following. Now, we explained that last week, but it's going to be nice to repeat it once again. For the FF value, we're using this table, okay, which is going to help us on classification of the powder flowability according to its flow index, or the FFC. So the flowability is going to be hardened if the FF value is going to be less than 1. It's going to be free flowing if its value is going to be more than 10. And the cohesive is going to be if the value is going to be less than 4, very cohesive less than 2, easy flowing if it's going to be less than 10. To do the process and determine the outlet Hooper, we usually going to follow the American Society for the Standardization, number D6128 version 16, with standard decimeter for the shear testing of the bulk solids using the Jenkins shear testing. Multiple measurement has been done, and we have a chart. We can use it for the niche design of the different to make the design for the Hooper outlet. The two charts we are going to use for the solution of the design procedure in our assignment and in the future, and that's why I shared these charts with you, and I would like to keep it for the future work, are the following. First, that's what we call it the Jenkins equation for the flow factor. You have to be based on that. Okay, we have the FF value has been tabulated on the right axis, y-axis of the chart. On the left axis of the chart, we have the wall fraction in degree. Here we are going to have the D. Here we are going to have the D. And these are what we call the wall fraction curves. Okay, this will only the wall fraction. And here we have the symmetrical angles in degree. So we can use this table, as I'm going to explain to you in the following example, if we are going to have the wall fraction angle and we have the flow factor curve, we can simply find the value for the symmetrical angle theta, and we can find the flow factor FF, and we can use it for the later stage of finding the parameters to design the minimum diameter of the Hooper. You can see that this chart actually is for the symmetrical sloped outlet only. Okay, symmetrical sloped outlet only. Now we said that most of the Hoopers are going to have the conical shape, so we have another chart for the conical outlet Hoopers. Just this one. The concept is the same. We need to find two parameters, and we're going to find the other term. Okay, we need to find two parameters, which are going to be mainly the W and the delta, and we can find the theta, and we can find the FF, and use it in the later stage of the design. So we said earlier that as the time passing, the constellation will be happening. And thus we are going to require a bigger diameter as the storage time is going to get longer. So the diameter, and actually you can see that later in your calculation, the diameter required to empty the hooper when the material has been stored for 1 day is going to be smaller than the diameter to empty the material which has been stored for 4 days. So usually we take the range. We take, for example, that the maximum period for the storing is going to be about 5 days. We design the minimum diameter according to the 5 days time. So these are the charts once again, and actually you can find it at the end of this slide. For full size, you can print it. But actually, I showed it on the canvas, so no need to do that. Now, to find the CAS value or the critical applied stress, okay, we need to do this sketch. We do the things graphically. We calculate the line between the sigma and the tau, starting from the origin, and we are going to use the MFF. Okay, we sketch the MFF, and we use the value of the FF from the previous chart, and we sketch the line starting from the origin. The intersection point between them is going to give me the value of the CAS, or once again, the critical applied stress, which is going to be very useful to decide what will be the minimum stress required to start the material moving within the system. So the stress in the outlet of the hooper may drop below the CAS value if the opening is going to be too small. Hence, the outlet opening size must be ensured that the applied stress must exceed the critical value. Something like, that's the critical stress. If I'm going to just push it, the material starts to flow. If I'm below it, the material is still static. So the correlation relating the outlet size to the CAS provided. Higher CAS value, larger diameter of the system. So once again, we said to find the value of the CAS, we first sketch the MFF, the material flow factor curve, and this can be found by knowing what will be the compacting stress against the yield stress. I can show that in an example. We know the delta and delta W, and we can find the value for the FF. We sketch a line that tangent is equal to 1 over FF starting from the origin. The intersection point is going to give me the value of the CAS. The CAS is going to be applied in the function to calculate the value of the known diameter with the use of theta we found from the same two charts. So the function in flow, once again, is going to have the time function in flow, and we have the flow function. And this, you can see that actually the stresses are going to be higher as the time is passing. Now we learned how to find the CAS. We learned how to find the theta. Okay, and we're going to use this parameter to calculate the diameters of the outlet. So first we start with the conical hoopers. Theta is this angle, semi-inclined angle, and we found that actually in the chart we just described. The D is the diameter of the outlet. D can be found by multiply the H theta by the CAS divided by the density multiplied by the G divided by the GC. The H theta for the conical hoopers is equal to the 2 plus theta divided by 60. How to get the theta? From the figure 1017 or 1018. 1017, we're going to have the symmetrical outlet. 1018, we're going to have the conical outlet. H theta is constant, which is going to be a function of the Cooper angle, and the typical value for the H are going to be about 2.4, which is more than 1 for the rigid Cooper and more than 2 for the conical Coopers. I prefer the 2 calculated. For the symmetrical hoopers, the equation is going to be, we are going to have width and we're going to have length. We can calculate the width, and the length is going to be 3 times the width. The width is going to be equal to the H theta multiplied by the CAS divided by the density multiplied by the G divided by the GC. Now the H theta is going to be different. It's going to be 1 plus theta divided by 180. The H theta function is going to be different depending on the shape of the outlet. For the circular, it's going to be the highest. For the square, it's going to be less. And for the rectangular outlets, where the length is equal to more than 3b, is going to be the least. So, of course, there are the minimum dimension. These are going to be the minimum dimensions. So, if I'm going to have, for example, the dimension to be 100 millimeter diameter, this will be the minimum thing I'm going to have. Of course, I need to go a little bit more. So, in the next section, more correlation are going to be given for the estimating of the flow throughout the solids through the opening. And for the larger opening may be used for the greater throughputs actually, and still maintain the massive flow. In a practical design, the angle of theta is reduced by 3 degrees as a margin of safety. So if I'm going to have it as 27 degrees, I usually going to use 24. Now we are going to have an example. This example is not going to be exactly like the one we are going to have in the assignment, but I'm going to give you more examples on that. So we have the shear stress and the yield stress for the junkie yield versus plots for a certain material yield in the data shown in the table. We're going to see it next. Determine the wall slope and the opening size to ensure the massive flow in the conical hoopers for this material, assuming that the density for the material is going to be 1,300 kilogram per cubic meter. Now, the introduction of this equation is similar to the question we had in the assignment. We know the density of the material, and we have the measurement value by using the Jenkins yield versus test. So this will be the table. We have the sigma 1 and we have the sigma c for 4 sets of testing. We start first with the lower stress. We got lower critical stress. We're increasing the load, and the sigma c is also increasing. Now, for the wall friction measurement, we did 2 measurements. First one, the normal force was 2, and we got the shear force was 0.689. For the second time, we increased the normal force and it became 3, and we got that the shear force became 1.03 kilopascal. Now, the effective angle of the internal friction for the material by itself, we're again to have it as the delta y over delta x. That means we got this value from the sketch itself. The difference between the slope of the line we had, delta y was 1 kilopascal, and the delta x was 1.73. So, of course, from there directly we can find the tangent of the delta, and then we can find the delta of the internal friction directly. So we have such results. The one we had in the examples are quite similar. It's not that much difference. Again, to show you that as we're moving. Where is the canvas page? Okay, so the Canvas page, I'm going to show you the assignment question before we're going to go forward. Okay, so what we have here is a table for the results. Okay, so we have 3 days testing. For each time we calculated the normal stress and the shear stresses. Now, in that case, we need to make 3 more circles. From 3 more circles, we're going to find the sigma C and the sigma 1. And then we are going to go from there to calculate the other things. For the wall fraction measurements, we have, once again, 2 measurements. From there, we can find the deltas and calculate the delta of the delta value. And I'm going to show you how to find the delta W, find the delta, and the delta W, we can use the chart to find the FF and theta, and then continue the calculation from there. So the only difference between the example we saw and this question is that we don't have the delta W. We need to find delta W by a graphical method. So go back to the example we have here. Okay, so once again, what we can find here is delta W from here. I already can find the delta from here, and I can find the sigma 1 with sigma C chart, and I can find the CAS and find the diameter. So let's go through that. First, I'm going to find the effective angle of the internal refraction, which is going to be the tangent of the parameters we have. Tangent is always going to be the delta y, difference in the height, above the difference in the length. So it's going to be tangent of the delta is equal to 1 over 1.73, and this will be equal to 0.578. Of course, in that case, the delta itself is going to be the tangent inverse of this value. Okay, so we can find delta, which is going to be equal to 30 degrees. Now, I'm going to use the other 2 parameters for the wall refraction test to find the wall refraction angle. Just remember, this is delta, and I'm going to find the delta W. For the wall refraction measurements, we have 2 parameters, 1 and 2. Okay, if I get to extend this line, it's going to take me to the 0 or the origin. Now I have this line. I got this line once again from the parameters we had in the table here. We had the normal force 2 against the shear force of 0.689, 3 against 1.43. Okay, so these are the 2 values, and as you can see, because we have 2, 3, we have 0, 1, we have the line to start from the origin point. Now, from which this diagram, I can see the data are going to be linear, the angle is going to be easily found from the rays run as before. So I only need to find the tangent of this curve. I doesn't have to start actually from the origin. Simply I can say that the delta y over the delta x is going to be tangent of the delta w, and then I can find the value of the delta w by doing the tangent value. So the delta w is going to be equal to the tangent inverse of 0.433, and plus is going to be equal to 19 degrees. Now I have 2 values. 19 degree for the delta W and 30 degree for the delta. Now I'm going to put it in together, and I'll start to calculate the theta and the FF value. Now we're going to learn how to use this chart. So for the design chart, I'm going to consider that it's going to be a conical outlet. Okay. And I'm going to do my calculation. First, I'm going to locate the delta W on the chart, 19 degree. 19 degree. So you can see that every step here is going to be 2 degrees. 12, 14, 16, 18. In the middle is going to be 19. From here, I'm going to locate delta W lines, which are 30 degree on both lines. This is 30 degree, and this is 30 degree. I'm going to start do the intersection between the 19, sketching a horizontal line is going to be intersecting with the 30 degree lines we have here. This will be the intersection point. Now from this intersection point, I'm going to sketch a vertical line to be intersecting with the x-axis to find the value of the theta. Okay, find the value of the theta. Now you can see that the value of the theta is 25, 26, 27, almost 28. Now I'm going to sketch a vertical line from the theta going up, intersect with the flow factor curve here. Now you can see that the intersection is going to be here. I'm going to sketch a horizontal line from here to find the value for the FF. Okay, so here I can say that the theta was 0.28 degree and the FF is 1.84 unit less. Now I'll go for the steps on using the chart again because this will be very important. You are going to need it for the assignment, you're going to need it for the Monday exam, and you're going to need it, of course, for your practical life. We had the lab, the measurement parameters, okay? Then we are going to start calculating the delta W and the delta. Why? Because the delta is here, delta W is here, and we are going to have two parameters to find the other two parameters that cannot be found directly, the theta and the flow factor. So we take a look to the chart. Locate delta W. Locate the two lines for the delta. Sketch a horizontal line starting from the delta W value. Intersect with the delta curve. Sketch intersecting. Now from here I will go down to the y-axis, to the x-axis, to find the value of the theta, 28. Now I'm going to extend this line until it's going to intersect with the flow factor curve. Okay, and I'm going to have another intersection at that point. Now I'm going to sketch a horizontal line to intersect with the flow factor line. I got the value for the FF, which is 1.824. So I got these two values, and I'm going to use them to continue the calculation I need to find, which is mainly the CAS value. So I had the FF. The slope of the line I'm going to be sketching is going to be equal to 1 over FF. The other parameters, or the MFF, is going to be using the data we got from the table, which is the sigma 1 and the sigma c, to sketch the curve. These values are going to be intersecting to allow me to find the CAS value. So the VS delta are going to be plotted, the sigma, this is sigma 1 data are going to be plotted to obtain the material flow function MFF, and the FF value is going to be used to plot the 1 over FF curve as seen in the following figure to obtain the CAS value. Now the blue points here are what we got for the sigma 1 and the sigma c for the 4 different stresses. We said once again we were increasing the stresses, and thus the yield stresses were increasing at the same time. So we got this curve. We sketch a line starting from the origin, having the slope of 1 over FF. this line will be intersect. By the way, if this line is going to be something like that, you can simply extend this line theoretically, and you're going to have the intersection. So if there's no intersection immediately, you make the intersection. Now we got the intersection, and this intersection will give me what the value of the cast or the critical applied stress to make the material move. Now, this will be the cast value. The cast is equal to 0.83 kilopascal. Now I know the cast value, I know the theater, I can calculate the minimum diameter in that case. Start first finding the H theater, which is equal to 2 plus the theta divided by 60. And then apply the equation that the diameter is equal to the H theater multiplied by the cast divided by the density multiplied by the G. So the H theta value is going to be equal to 2.647. And put these parameters in this equation, we are going to have that the diameter, the minimum diameter, is equal to 0.16 meters. Okay, now this is the minimum. Of course, we need to have a safety factor. So usually what we need to do actually is we take, for example, to 0.2 as recommendation. So hence the for the massive flow conical hoovers, the minimum diameters of the opening is going to be equal to 0.161 meters. The margin of safety, the semi-included angle is going to be reduced by 3 degrees, and the hoover design angle is going to be equal to 25 degrees. Now, the last part of this slide is going to be about the rate of discharge from the hoover. I prefer to leave this part for next week, and we start a tutorial based on what we just done right now, but it's going to be for the assignment number 1. Because I would like to start challenging yourself on do the calculation for the assignment number 1, question number 1, because actually question number 2, 3, and 4, just applying the equation directly or using some of the chart basics. But the number 1 is going to be a real life scenario on how to design the minimum outlet of the hoover design. So I'm going to stop the recording now. I'm going to have something like 5 minutes of break, and then come back with the tutorial, because maybe I'm going to extend it for you later if you're going to have time. So stop the recording.